we're taking the animation that we saw in the previous video now and sort of working it into the idea of calculus. Okay, so again, our goal is to have a whole bunch of sample rectangles that are very skinny, just like this green one right here. And we're going to revolve them around an axis of revolution. All right, when we make that revolution, all right, what happens is that rectangle turns into a cylinder. There's a lot of those cylinders because, again, we're looking at an infinite number of them in between A and B. All right, so these cylinders are actually quite thin, all right, and hence they're called discs. We think of them more as discs as opposed to cylinders, but they still have the cylinder's characteristics, including the volume of a cylinder, pi r squared h. All right, so we're interested in the volume of that cylinder, but again, we're going to add up the volumes of a whole bunch of cylinders. All right, so when we talk about what exactly is the volume, well, we know pi that's a constant, but then we have our radius. Well, the radius of the cylinder goes from the axis of revolution, which in this case is the x-axis, up to that point right there, which is our f of x. Now, if we found it at, if we had our rectangle right here, well, the rectangle would obviously be smaller than this green one right there. But this rectangle still has a radius from in between those two endpoints, which again is going to be the distance between the function and the x-axis. So it turns out that our radius, whether it's here or at the very end, our radius is going to be equal to the f of x, the function. All right. So as we're creating our volume formula, all right, well, instead of r, we have our function. All right. So since it's r squared, our function is being squared. Okay. Well, we also have our height. What's going on with the height? Well, the height is the thickness of this cylinder right here, right? Now we know that the cylinder is quite thin, all right? And there's just a little bit of the x-axis that represents the height, all right? A little bit of x or our dx there, all right? In the same way that the rectangles are very thin, so are these cylinders. So the height of the cylinder is actually represented by that little bit of x, that little differential right there. But that's important because, again, the volume is not just the radius squared, but the radius squared times the height. And of course, times pi as well. So we have our pi constant there too. Now, what are we looking to do? We're looking to find the sum of the volumes. So we have to add all these volumes up. There's our sum, right? From what range? Well, we want to begin at A and we want to end at B. So we just have our bounds of A and B. Okay. And again, using our properties of the definite integral, that pi, which is perfectly fine on the inside, can also be swung outside. So we have pi times the integral from A to B of f of x dx. So there's our formula for our volume. And again, because we're finding the sum of all of these cylinders, and these cylinders are very flat, so they're often known as disks, since we're finding the volume of the sum of the volumes of all these disks, this is often known as the disk method. All right, and the disk method is how we're going to calculate the volume of these solids in the next couple of examples.